Welcome to my classroom. In this chemical process calculation course, in the previous lecture, we have seen how to determine the heat of formation using Hess law, how to determine the specific heat of solids using Pope's law, and we have seen the theoretical background to determine adiabatic flame temperature. And we have seen that in an adiabatic system, the heat transfer between the system and the surrounding is zero. So that's why whatever is the energy transfer that is taking place, for example, delta H of the reactant. I have told you that we are bringing the reactants from the high temperature, whatever is the operating temperature, to the 25 degrees Celsius, whatever is the heat required, enthalpy required to reduce the temperature of the reactants from the T1 to standard temperature 298 Kelvin or 25 degrees Celsius. Then what is the heat of the reaction? And then heat required to raise the temperature of the products from 25 degrees Celsius to T2, what is the temperature of the products, right? So for that, these three should be summation should be equal to zero. Okay, we can assign the negative sign if the where heat is being removed, positive sign if the heat is being uh, raised. Okay, it is being added. Okay, so that way we have seen that how to do the how to determine the adiabatic flame temperature. I have explained in the previous lecture. Please go through it. In this lecture, we are going to discuss about how to solve the numericals if Cp is value is not directly given, but it is given as a function of temperature. For example, Cp equal to A plus Bt plus Ct square. So in that case, how to determine the Cp value at a known temperature? Okay, so actually this can be done. For example, we know the temperature T1 and the final temperature T2, and if we want to determine the Cp value at a intermediate temperature T, so there are two ways to do it. We can determine the Cp value at temperature 1 and determine the Cp value at temperature 2, and we can make an average to get the Cp at the given temperature. That is one way, and another way is we have an expression in terms of T, right? So what we can do is we can directly get a mean temperature between T1 and T2, T1 plus T2 by 2. Okay, so that way we get an average temperature. So that way you can substitute that mean temperature in the Cp to get a Cp value. Okay, so that way we can do. Otherwise, we can integrate the expression. Okay, we can integrate it Cp dt from between the limits of T1 and T2 to get the values. In all the ways, we can determine the enthalpy of the reactant or enthalpy of the product like that. Okay, we will start solving the numericals. If you have a gas mixture, how to determine the heat capacity? How will we determine the heat capacity? If you know the composition of a gas mixture, so we can determine if we can consider it to be an ideal gas mixture. So we can find the Cp of mixture by summing up the Cp of the individual components and multiplying it by the respective fractions. Okay, as I told in the previous lecture, if Cp is given in kilojoule per kilomole Kelvin, in that case your Xi is going to be mole fraction. If Cp is given in kilojoule per kg Kelvin, in that case your Xi can be mass fraction. Okay, so similarly delta H is going to be either mCp delta T or ncp delta T. So where Cp of the mixture is summation of product of Cp of the individual component multiplied by its fraction. Okay, mass fraction or mole fraction depending upon the value of Cp. Okay, so what if Cp is given as a function of temperature? For example, if Cp is given as function of A plus Bt plus Ct square form, so this A and Bc value may vary for different components. It can be given. Say for example, A equal to 2 plus 1 into 10 power minus 3t plus 0.8 into 10 power minus 6 t square. So in this fashion, if t value is C is given as a function of temperature, what we have to do is we can find delta H equal to, instead of MCP delta T, what we can do is Ni Cpi dt. Okay, so it can be summation of Ni Cpi dt, because Cpi is function of temperature and we know the component of I. Okay, so let me say that A1 plus B1T plus C1T square is component A, Cp of component A, and Cp of component B is given like A2 plus B2 T plus C cube T square. So what we can, how we will get this one is, so if you know the moles of A is Na, moles of B is Nb depending upon the mole fractions. Okay, so we can say number of moles of A, Na into Cp dt, right? So Na Cp dt, Cp of A dt plus Nb Cp of B dt. Okay, so that way you can get that Na is, N of A is, if known, N of A is N of A into integral of T1 to T2, if know the temperature T1 and T2, integral A1 plus B1T plus C1T square dt. Similarly, whatever is the number of component, it will go like this one. Same way, CNB into integral T1 to T2, A2 plus B2T plus T2T square dt. Okay. So in general, what is the integration? In general, what is the integration value? So after integration, what we are going to get is equal to Na into, after integration, if it is A1 into T2 minus T1 plus B1 by 2 into T2 square minus T1 square plus C1 by 3 T2 cube minus T1 cube. So, okay, same way we can write for this term also, NB also. Okay, so that way we can integrate it. So if you know T1 and T2, if T1 and T2, depending upon the formula given, it may be mostly in Kelvin. It will be mentioned while giving the data. Cp is in kilojoule per mole Kelvin, kilojoule per kilomole Kelvin. It will be given. So accordingly, this T is going to be in Kelvin, or it may be given that more calories per mole Kelvin, mole degree Celsius. In that case, T will be in degree Celsius. So depending upon data unit of Cp, we have to take care here. Okay. So if T1 Kelvin and T2 Kelvins are known, we can substitute to get here this value. So I can write Cp is equal to, okay, I can say Cp dt equal to integral Cp dt is equal to, actually what we will get, A into delta T we will get plus B by 2 into delta T square we will get plus C by 3 into delta T cube we will get. Okay, so between the limits T1 and T2, right? So if you substitute the values of T1 and T2, delta T is T2 minus T1, delta T square is T2 square minus T1 square, and delta T cube is equal to T2 cube minus T1 cube. So in this fashion, we can solve the problem. Okay, we'll proceed to solve this problem. So, so it is given that 26.03, right? So what is delta H? Delta H is equal to absolute enthalpy at two temperature 350 to 1500. It is heated from 350 degree Kelvin to 1500 Kelvin. Okay, absolute enthalpy at 1500 Kelvin minus absolute enthalpy at 350 Kelvin. Okay, so these are the two temperatures. Okay, so we have T1 equal to 350 Kelvin, T2 equal to 1500 Kelvin, and it is given the temperature of pure oxygen is raised from 350 to 1500 Kelvin. Calculate the amount of heat to be supplied for raising the temperature of 1 kilomole of oxygen. So here basis, what is our basis? It is given 1 kilomole of oxygen is our basis using the Cp data and absolute enthalpy data. Okay, so absolute enthalpy at 1500 Kelvin minus absolute enthalpy at 350 degree Kelvin delta H. Okay, so delta H is equal to what? N into Cp dt. Okay, So general formula I have told you just now. So here N is 1. So it is 1 mole, 1 kilomole, let us say 1 kilomole into Cp value is given. So let us write in the form of A plus Bt plus Ct square dt. Okay. So what we will get? Integral. We can do it like integral from T1 to T2. So integral T1 to T2. So that way what we are going to get is A into T2 minus T1 plus B into T2 square minus T1 square by 2 plus C into T2 cube minus T1 cube by 3. Okay. So this is what we are going to get in the general form. So here what is A in the from the given question we can write what is A, what is B, what is C, what is T1 and what is T2. Substituting delta H we are going to get. Okay. So here what is our A value? Refer to the question. So A is 26.03. So what is our B value? 11.75 into 10 power minus 3. What is C value? C is minus 2.34 minus 2.34 into 10 power minus 6. Okay. So ABC value we have, T1 value we have, T2 value we have. So we can get what is delta H. Okay. N is 1. That's why we are not multiplying by N here. So if you multiply also that is going to be 1. So substituting the values, what is N value? This is actually N into, for unit tally purpose we can keep that one. N is given 1 kilomole into A value is given, right, 26.03 into T2 minus T1. That and all you can determine if it is delta T, if it is delta T square and if it is delta T cube. You can determine the values of delta T1, delta T2 and delta T square. Delta T square, delta T cube. So easy for us to substitute if you are performing in this fashion. Otherwise you can simply substitute directly also to get the answer. But if you want to verify it, it's better we write that one. 1500 minus 350 is equal to delta T. What is that? Use your calculator. 1500 minus 350 is equal to 1150. Okay, 1150 plus B by 2. What is B? 11.75. Okay, 11.75 divided by 2 is 5.875 into 10 power minus 3. 5.875 into 10 power minus 3 into what is delta T square? Delta T square is you can determine, that is 1500 square minus 350 square. How much? 21, 27, 500. 21, 27, 500. So similarly, if we calculate the value for T cube, what is T cube? 1500 power 3 minus, what is that? 350. 350 1500 power 3 is the other calculator. 1500 power 3 minus 350 power 3 is equal to some big number. 3332125 Okay. So if you substitute this value, you are going to get the answer. Here what is C value? Minus 2.34 into 10 power minus 6 into 3332125. I can divide this by this
multiply by 2.34. What we get is, third term is, I'm just writing so that you can verify the steps. Okay, 7797.1725 is the step. Similarly, what is the second value? This is minus, right? Remember, minus is here. Similarly, what is the first one? 26.03 into 1150, which is 29,934.5. Okay. Similarly, here we are having 2127,500 into 0.005875. So 12,499.1. So what you get is 39,834.6 kilojoules. Okay. So this is what we get. We can solve the same if absolute enthalpy of given. For example, second example, you say if absolute enthalpy is given, absolute enthalpy of oxygen at 1500 Kelvin is 49273, at 400 Kelvin is given like 8597, and at 300 Kelvin it is given 11603. All are in kilojoules per kilomole. So how will you find the enthalpy change? How to do that? So we can do in this fashion. Absolute enthalpy at 1500 degrees Celsius. So here we have data are 300 and 400, and for this we are having data directly, as I told. So we can find the data enthalpy value of 350 degree, because our system is at 350 Kelvin, 1500 Kelvin to 350 Kelvin. So to heat it from here to here, what is the heat requirement? We can determine using this value. Absolute enthalpy of hydrogen is given. Okay, so if it is given, we have data for 1500 directly, but for 350 what we can do is we can take an average of it, because average of temperature 300 plus 400 by 2 gives 350. Therefore we will have 11603 plus 8597 by 2 is equal to, so what we will get is 10,100 we will get. Okay, so same units, kilojoule per kilomole. Okay, so what is the delta H? Delta H is equal to enthalpy at 1500 degrees Celsius minus enthalpy at 350 degrees Celsius. So enthalpy of 1500 degrees given 49273 minus 10,100, so which gives us the value 39,173 kilojoules. Okay, so we have 1 mole, total is 1 mole, right? Multiplying by 1 kilomole. Okay, so multiplying by 1 kilomole, so we get answer in kilojoules. So this also, this is 39,173. What we got is 39,834. So we are getting almost close to 39,000 by both methods. Okay, so this is what we can do when we know data at two different temperature, but what we want to CP enthalpy value at a mid temperature of 350 Kelvin. So always we can go for taking an average value. Okay, so just like y2 minus y1 by x2 minus x1. So that way we can get the value in between also. Okay, so this is what we have done in this problem. Okay. We will do a numerical on determining the specific heat capacity of a gas mixture. Okay, let us have a gas mixture of component A and B. How to do it? I told you that if a gas mixture is containing A and B, let mole fraction be x and 1 minus x. It's a binary, summation of mole fraction should be equal to 1. So if you know the mole fractions, and if you know the total moles, we can get how much moles of A is present, how much moles of B is also present, right? So if you say total moles is n, then number of moles of A is equal to XA into n, and number of moles of B is equal to XB into n, where XB is XA plus XB equal to 1, therefore XB equal to 1 minus XA. So that way we will get what is the number of moles of A and number of moles of B, we know. And Cp of A is given as a function of A plus Bt, and Cp of B is given as a function of another, let me say A1 B1, it is A2 B2 T. Okay, so it can be go up to any way. Okay, C1 T square plus C2 T square. So it can go, this is expression, like Taylor series expansion, it can be going further, but it is up to our convenience. We can stop up to T square or we can stop up to T depending upon the requirement, how we are doing exact analysis or approximate analysis. Okay, so then the enthalpy of the mixture is given by, or you can say H equal to MCP delta T. Here NCP delta T, where the individual components are there, so we can say Na into Cp delta T plus Nb into Cp delta T. If Cp is directly given, we can directly substitute to get the value of enthalpy. But whereas if Cp is given as a function of temperature, Cp is given as a function of temperature, if Cp is equal to function of temperature like this, so then we have to substitute in the equation to get that one. That is Na multiplied by integral A1 plus B1 T plus C1 T square dt between the temperature T1 and T2 plus Nb into integral T1 to T2 A2 plus B2 T plus C2 T square dt. Okay, so after integration, what will happen? So if we integrate this, what we are going to get? A1 T2 minus T1 plus B1 by 2 T2 square minus T1 square plus C1 by 3 T2 cube minus T1 cube. Okay, similarly we can write for NB into same terms. Similar terms will come with the A2, B2 and C2 terms. Okay, so that way we should be able to solve numericals. Okay, so we will do a numerical on this fashion. Take down a stream flowing at a rate of 500 moles per minute containing 35 mole percent nitrogen gas and 65 mole percent hydrogen gas. 65 mole percent hydrogen gas is to be heated from 25 degree Celsius to 200 degree Celsius. Calculate the heat that must be transferred and Cp data is given to be transferred. Full stop. Cp of Na is given as 5.4 plus 1.2 into 10 power minus 3, and Cp of H2 is given 7.8 plus 2.6 into 10 power minus 3 T, where Cp is in calorie per mole Kelvin. Okay, so we are having mole only, so that we no need to convert anything. And T is in Kelvin. So this is the given data. I repeat, a stream flowing at a rate of 500 moles per minute is containing 35 mole percent nitrogen gas and 65 mole percent hydrogen gas is to be heated from 25 degree Celsius to 200 degree Celsius. That must be heated from 25 degree to 200 degree Celsius. Calculate the heat. Calculate the heat that must be transferred if Cp of nitrogen is 5.4 plus 1.2 into 10 power minus 3t. Cp of hydrogen is 7.8 plus 2.6 into 10 power minus 3t. Remember, as I told, this expression can be A plus Bt. So here we are having Cp as a function of A plus Bt, right? So we are not having C plus T square. So that is, this is going to be simple calculation. Okay. So what is the basis here? We are having a basis of, to solve, basis is 500 moles per minute. Okay. So we are having 500 moles per minute of gas mixture. Right. So we are having 500 moles of gas mixture. So that means that it is containing A and B, right? So what is A? Let me say A is nitrogen and B is hydrogen. So we are having the fractions here. My fractions are given. Nitrogen is 0.35, hydrogen is 0.65. Total should be 1. Yes. So that way amount of number of moles of A is equal to number of moles of A and number of moles of B is equal to 0.35 into 500. How much? 175 moles. So we have 175 moles of nitrogen and 500 minus 175, 325. We have 325 moles of hydrogen. So this N value, Na and Nb we have, I told you, NaCp of A dt plus Nb Cp of B dt from T1 to T2. Right? So this will give me the heat to be removed or added to the system. Okay. So the heat transfer, how much heat is transferred can be determined using the Cp data. Okay, so we have Na value 175, Nb value is this. Okay, so in general, what is the formula? We have Cp equal to, in general, let Cp is equal to A plus Bt. So what is integral Cp dt? We are going to get from T1 to T2 means what we will get? So we are going to get A into T2 minus T1 plus B into T2 square minus T1 square, which we can written as A into delta T plus B into delta T square. Okay. So if we substitute that here, what we will get is Na into A into delta T plus B into delta T square. So let it be A for A and B for A plus NB into same formula. So we'll have A of B into delta T plus P of B into delta T square. Okay, so we have both temperatures, right? So it needs to be heated from 200 degree and 25 degree. 200 degree Celsius, 25 degree Celsius. Okay, so but we should write them in Kelvin. T is in Kelvin in Cp. So therefore, T1 is equal to 200 plus 273, which is 473 Kelvin, and T2 is 25 plus 273 is 298 Kelvin. So we have T1, T2. Will you determine delta T first? And delta T square equal to, so delta T is 473 minus 298, we will get 175 Kelvin. Similarly, what is delta T square? 473 square minus 298 square. Remember, it is not delta T whole square. It is delta of T square, which we, for our own convenience, we are writing. Otherwise, we have to substitute in detail in the equation. You will get a lengthy expression. To simplify that, I am using like that. So, what is the value of this? So, we can determine 473 square minus 298 square, which will be 134925. 134925 Kelvin. Okay, Kelvin square. Whatever, you don't mind about units. Okay, so now will you substitute A and B value? What are the A and B values? We can write it from the given data. So this is AA. AA is there. BA is this. AB, and this is BB, where A and B represents component nitrogen and hydrogen. Okay. So substitute A value, B value. Let me write it and take it there. AA equal to 5.4, BA equal to 1.2 into 10 power minus 3, AB is 7.8, BB is 2.6 into 10 power minus 3. So use the substitute the values to get the answer. Okay. So what you will get? So get the value for Na. Let me write it as two terms. Okay. So what is the value for the first term plus second term? Okay. So first term value will get in calories. We are going to get. Okay, calories plus this much calories. So we can write the answer in kilocalories. So totally you will get, first term you will get 179.542 kilocalories. In second term you will get 500.631 kilocalories. And please comment your final answer. If you are getting whatever you are getting, so that kilocalories, please comment your answer, please. So you will get around 680.2 kilocalories. Okay, please post your. So look at this problem. Calculate the heat input to raise the temperature of 128 kg of SO2 from 373 Kelvin to 1273 Kelvin. Perform the calculation by integration method. Perform the calculation by integration method. That is one way which we know. And perform the calculation by integration method is integral Cp dt T1 to T2 we can do. Cp mean value is Cp mean is equal to integral Cp dt T1 to T2 by T2 minus T1. So this is the way we can determine the Cp mean value. And another way method is using the Cp value at mean temperature. What is mean temperature is temperature mean is equal to, so we assume Cp is given as A plus Bt plus Ct square. So we have Cp T mean is equal to T1 plus T2 by 2. For example, T1 is 100, T2 is 200. So we'll have 150 as the T mean. Okay, so this is an example. So here the temperatures are given as 373 Kelvin and 1273 Kelvin. Okay, let's solve this problem. So to solve that, so we have temperature given. So let us Cp value is given. Actually, the question is incomplete. So we have Cp of SO2 is given as 6.85 plus 8.533 into 10 power minus 3 T minus 2.475 into 10 power minus 6 T square. Okay, so we have expression where we have A is equal to 6.85, B is equal to 8.533 into 10 power minus 3. So for easy substitution purpose, you can write like 00853, and C is equal to minus 2.475 into 10 power minus 6, which we can, for simply substituting, we can write 5 zeros into 2475. Okay, so that I can use the normal calculator. Okay, ABC value we have, and we have T1 value. What is T1? 373 Kelvin. What is T2? 1273 Kelvin. Okay, so if T square is involved, we are going to make use of three terms. That is, we can determine delta T1, not delta T1. We can determine delta T, which is T2 minus T1. Can substitute this much Kelvin, and you can find substitute to get delta T square, that is T2 square minus T1 square, which will be 1273 square minus 373 square. You can have this much Kelvin. Similarly, delta T cube equal to T2 cube minus T1 cube, which is 1273 cube minus 373 cube. You can calculate these values and keep it ready. Okay, so we can solve the problem. How to solve the problem? So perform how much, what is the heat input to raise the temperature from 1 to, so heat required delta H is equal to a single component. So we can, since it is single component, only one component is there. There is no Na and B involved. There is only one. So N into Cp into dt. Okay, Cp is given as function of temperature. So where N equal to A plus Bt plus Ct square dt integral T1 to T2. Integral T1 to T2. So what we will get is, we will have N equal to N into, so integration of this A into dt is AT, and T upper limit and lower limit, what we will get is A into T2 minus T1 plus B into T2 square minus T1 square by 2, okay, plus C by 3 into T2 cube minus T1 cube. Okay, so which I can write as N into A delta T plus B by 2 delta T square plus C by 3 delta T cube. Okay, so now we have all the values. What is N value? Is our basis. Our basis is to be, it is mass is given. Okay, mass is given 128 kg. So we should correct it to mass by molecular mass of SO2. We will get the value. So 128 kg divided by, what is the molecular weight of SO2? Molecular weight of SO2 is 64. Okay, so 64 kg per kg mole, we will get this much kilomoles, kg moles. Okay, so what is the N value? Please determine. 128 by 64 is equal to, it's half of it, right? Almost 64 into 2. So you'll get N equal to 2 kg moles. So we have all the data now. ABC value you have. Okay. ABC value you have delta T square value, delta T cube value. Please determine and write those values and we can get the answer. Okay. What is that? 1273 minus T73 is 3 minus 373 is equal to 900 Kelvin. I am doing this step by step just so that you can verify the answers. Okay. So once you are thorough with the procedure, you can directly write the terms, lengthy terms, and you can get the answers. Okay. So here, what is the square term? 1273 square minus 373 square is equal to 1481 400. Similarly, this is going to be a very big term. 1273 power, sorry, not square. 1273 power 3 minus 373 power 3 is equal to 201103. Okay, so we have ABC value. You can determine, you can substitute the formula here, right? So you can take this data. Okay, keep like this, I can use. Okay, so we can substitute N equal to 2 kg moles into A value is 6.85 into delta T value is 900. Okay, plus B by 2. What is B value? By 2 into delta T square value 1481 400. Okay, and C value is minus 2.475 into 10 power minus 6 divided by 3 into this value. Okay, so if you write step by step, we can verify later. That's why we have to write like that. But if you directly write this delta T terms in this and directly get also okay. So now we have, so what is the CP value? Formula is given that CP is in, it is given that CP value is in calories per mole Kelvin. Calories per mole Kelvin. CP is given calories per mole Kelvin. That means equal to kilocalorie per kilomole Kelvin. So that way this kilomole gets cancelled. Okay, so delta T also we have multiplied by delta T. So what we get is this much kilocalories. Okay. Please comment your answer. So whatever you will get, you can write the value. Okay. So that is the first part. What is the second part? Second part, it is asked to use using CP mean value. Okay. What is using CP mean value? CP mean is equal to integral CP dt by T2 minus T1. Okay, so this part already we have calculated. Okay, so this is actually we can write like 2 into the values, then final answer. So whatever value you are getting here, so this can be this numerator. Okay, so that way, so we will get 2 into 10,826. Okay, so here we have that value. So CP mean equal to 10,826 divided by T2 minus T1. What is that? T2 minus T1. We have 900 degrees Celsius is delta T. Okay. So what is the value? Please use your calculator. So you will get around 12.03 kilocalorie per kilomole Kelvin. Okay, it's calorie per mole Kelvin. I can say kilocalorie per kilomole Kelvin. Now substituting in delta H equal to Cp delta T. Now if you substitute delta H equal to Ncp dt. Okay, so N is 2 kilomoles into Cp mean is 12.03 into Tt value is 900. Okay, that is T2 minus T1. Okay, so we will get delta H value here. Okay, so again we will be getting an answer around 21652. Okay, so now this is second method. First method whatever answer you commented, you are going to calculate, and that you can compare here also. So here delta H is equal to this much kilocalorie per kilomole Kelvin. It's not Kelvin. When you multiply by delta T, you get that one. Okay, so now the third method is calculating the T mean value, which is T1 plus T2 by 2. How much? 1273 plus 373 by 2 is 823 Kelvin. Okay, so using this T mean value, you can determine the Cp. So what is the Cp value at T mean? Cp of SO2 at T mean. Okay, so Cp value is given, right? Write the given expression Cp equal to, from the question you can write 6.85 plus 8.533 into 10 power minus 3 within bracket, substitute the T mean minus 2.475 into 10 power minus 6 within bracket, substitute the T mean value whole square. So that will give us a Cp value. Please calculate. So you can calculate the Cp value by substituting in Cp at T equal to 823 Kelvin, which is A plus Bt mean plus C into T mean square. Okay, just substitute the value of A, B and C. Okay, so you will get this thing, that is 6.85 plus 8.533 into 10 power minus 3 into 823 minus 2.475 into 823 square will get you will get a value of Cp value, which is kilocalorie per kilomole Kelvin. Okay, so again to get delta H value, delta H equal to Ncp dt. So you will get N value is 2 kilomole into Cp is whatever you get, you substitute, its unit is kilocalorie per kilomole Kelvin into delta T. Delta T is 1273 minus 373. 1273, that is 900, right? 900 is the Kelvin. So Kelvin get cancelled, kilomole get cancelled. You get delta H equal to this much kilocalorie. Okay, so you will get around 22,000 plus or minus 100. Okay, so these are the three ways we can use to determine the enthalpy, that is heat input to raise the temperature from lower temperature to higher temperature. First, fully you can do it by integrating total delta H term, or simply determine the Cp delta T and then get the Cp mean value, then substitute in delta H, or directly you can use a mean temperature. First obtain a mean temperature and substitute in Cp to get the enthalpy. Okay, so these are the various ways by which we can solve the problems. Okay, so we have seen that when a fluid, when a substance which may be in solid state, Okay, so if it is heated, what will happen to the temperature? When you are raising the temperature, the sensible heat is can be measured. That is, we can measure the temperature change in the system. But whereas once it reaches a temperature of, say for example, let us consider the case of water. So when it is in ice form, so when you are reducing the temperature from minus 20 to 0 degree Celsius, what will happen? We can sense the sensible heat. But at 0 degree Celsius, there will be latent heat of fusion. So this ice will become water, and that's why whatever heat is supplied is used for a phase change. But after that, 0 degree, from 0 degree to 100 degree Celsius, it is purely water. That's why we can have a sensible heat, that the temperature can be measured as heat is added to the system. Okay, once we have reached 100 degree Celsius, then further heat that is added is only used for phase change. So that way we will have sensible heat on latent heat of vaporization. And then further again, if you are increasing the temperature of the steam from 100 further to further temperature, we are going to have sensible heat. So totally, when you are heating from a minus 10 degree Celsius to, so let me say, minus 20 degree Celsius to 130 degree Celsius, totally how many sensible heats are there and how many latent heats are there from solids to vapor? Okay, so how many sensible heat is there? This zone is sensible heat, one sensible heat. Okay, so again we have another, here to here there is sensible heat, and from here to here there is one sensible heat. So totally we are having three sensible heat, that is the MCP delta T or NCP delta T coming into picture, sensible heat, which can be calculated for change in temperature. And how many latent heats are there? So here the flat profile is one, so here there is one another profile. So there will be two latent heats. One is latent heat of fusion, another one is latent heat of vaporization. So totally we will have five heat terms, five enthalpy terms will be there, out of which three sensible heats and two are latent heat. Okay, so we will do a numerical on this part actually. Hang on. Calculate the heat added to 100 grams of water to heat it from minus 20 degree Celsius to 130 degree Celsius at 1 atmospheric pressure. Remember, boiling point is a function of temperature. Boiling point temperature will change with pressure also, right? So some data is given. Specific heat of ice is equal to specific heat of ice is equal to 0.485 calorie per gram degree Celsius. Remember, now MCP delta T we have to use because specific heat is given in calories per mass values. Okay, so specific heat of ice, specific heat of water equal to 18.03 calories per gram degree Celsius. And similarly, for steam it is given as a function of temperature. Specific heat of steam is equal to 7.256 plus 2.298 into 10 power minus 3 T plus 0.283 into 10 power minus 6 T square. Okay, by this time you might have observed that A value will not have any exponential term. A second term B will have 10 power minus 3, C term will have 10 power minus 6. That is a general trend we have observed. Okay, so all these values are in calories per mole degree Celsius. So, but for steam it is given calories per mole degree Celsius. So we are having data 100 grams of water. We know mass is 100 grams. We know what is molecular weight of water, 18 gram per gram mole. So we can get N value 100 by 18 gram per gram mole. this gram will get cancelled, so we will get 100 by 18 gram moles. Okay, so whatever is the value, you can report 100 by mixing how much, 5.55. Okay, so n value we have, so that n value we have to use NCP delta T for steam. When you are calculating specific heat, we have to multiply by that value correspondingly. So that's why I always tell you, check the value of CPs, what data it is given, unit, associated unit it is given, we have to consider. Okay, so other two data are also given. Latent heat of fusion of ice, latent heat of fusion of ice is equal to 1436 calories per mole. Remember, again for this also unit is mole, so this multiplied by number of moles gives us the latent heat of fusion of ice. Okay, and similarly latent heat of vaporization of water, latent heat of vaporization of water is equal to 9717 calories per mole. Okay, so all data is given, only we have to substitute, we have to determine 3 sensible heat, and so only we have to determine the 3 sensible heats and 2 latent heats. Summing it will give us what is the total heat to be added. Okay, we can write like heat to be added is equal to, you remember the diagram which we have seen already. Okay, we have to find each one of them. Okay, so what are the terms? Total heat added, total heat to be added is sensible heat first, sensible heat to bring the ice from -20 to 0 degree Celsius, right? That is one sensible heat. Then we have latent heat of fusion, which takes place at 0 degree Celsius, plus again sensible heat to heat the liquid from 0 degree to 100 degree Celsius. Okay, plus again latent heat of vaporization at 100 degree Celsius. This is what takes place here. Okay, so then again further we have sensible heat of to heat the sensible heat to heat the steam from 100 degree Celsius to 130 degree Celsius. In this, for only for steam we have to determine as a function of temperature, so that Cp delta T formula integration we will do from 100 to 130. So remaining are directly given, you can calculate. Okay, mCp delta, either you have to make use of mCp dt or ncp dt, or simply n into lambda, n into lambda. Okay, latent heat of fusion, n into lambda vaporization. Okay, so these only formulas make use to calculate the answer. Okay, please report all the 5 terms. Let it be for term 1, be for term 1 plus second term, third term, fourth term, and fifth term. Okay, so please write each one and report your final answer. Okay, so you are going to get above 70,000. Okay, so we will get an answer of about 70,000. So please comment your answer. Okay, so if you have calculated yourself, comment your answer. Okay. Thank you for joining my classroom. In this lecture, we have discussed about, that means we have solved numericals on determining the sensible heat, latent heat, specific heat. If Cp is a function of temperature is given, how to determine the Cp mean value or Cp value, or if a mixture of gas is given, how to determine the specific heat value for the products, that we have done. Okay, so in the next lecture we will solve numericals on adiabatic flame temperature. Already we have crossed 1 hour, so I will proceed with numericals on adiabatic flame temperature in the next lecture. So if you have any doubts, please contact me, and please leave a comment. If you have got the same answers, you can comment your answers also. Thank you for joining my classroom.